Modern market competition requires massive capital investment in data science. Deploying artificial intelligence and machine learning is now viewed as a mandatory survival tactic, driving organizations to acquire as much raw compute power and algorithmic talent as their balance sheets allow. A 2020 Cognilytica survey reveals 90% of businesses expect an in-progress AI implementation within 2 years. But adoption hasn't guaranteed success. McKinsey data shows 86% of executives report their organizations are only somewhat effective at meeting their data objectives. This creates a startling disconnect. Why do mathematically sound, rigorously tested machine learning models routinely fail to survive the transition into a corporate business environment? To understand the failure, we have to look at how data science functions as an umbrella term. This visual shows it as a field of inquiry focused on extracting meaningful insights through 3 distinct subfields: data analytics, machine learning, and artificial intelligence. When projects in these fields collapse, the postmortem rarely points to a lack of technical tooling or deficient engineering talent. In most cases, the code itself is functional. The collapse is typically strategic. Technical proficiency does not translate into business value without a rigorous execution framework designed to bridge the gap between a model and a market. Look at a standard corporate organizational chart. In many companies, the data science team functions as an opaque, isolated unit. They operate on the periphery, structurally disconnected from the core business units that drive the company's revenue. Organizations attempt to bridge this distance by spending heavily on environments like Python and Tableau. But access to a dashboard doesn't create profitability. This isolation creates an execution gap. Models run locally, but outputs hit a structural wall before functional units can integrate the insights. To bridge this gap, technical potential must be measured against a clock. Organizations need a formalized 100-day evaluation and deployment roadmap, a time-bound sequence that forces a project to move from a theoretical experiment to a deployed asset. This roadmap forces technical teams to align their work with the C-suite's top-line profit and loss objectives, ensuring that every algorithmic update serves a documented business need. Investing in data science tools without this sequencing roadmap is a sunk cost. It ensures the project will eventually join the 86% of initiatives that fail to deliver a return. In any given quarter, a technical team can generate dozens of potential data science use cases. To avoid wasting capital, leaders must act as gatekeepers, filtering these ideas before any development begins. This criteria lists the 4 foundational prerequisites that every proposed data science project must pass to be considered viable. First, the required data must be actively available and accessible. Second, the organization must have the specific human capital in place to execute the build. Third, the initiative must strictly align with current strategic priorities. Finally, the technical architecture must be capable of supporting the deployment. If a proposed model fails even one of these 4 checks, it is discarded. Ruthlessly filtering projects at this stage preserves capital. It prevents teams from spending months building technically perfect models that the business is structurally incapable of using. Even with strict filtering, a business may have several viable projects that pass the initial gates. Because bandwidth is finite, the organization must determine which single project to tackle first. This is the Data Science Opportunity Matrix, the primary tool executive leaders use to score and rank surviving projects against one another. The x-axis measures feasibility, a calculation based on the estimated time to deploy and the total financial investment required. The y-axis tracks business value impact, weighing a project's potential for revenue generation or cost reduction. These specific metrics are used to calculate a project's exact position on the matrix. By assigning 1 to 5 ratings to implementation complexity, certainty of value capture, and magnitude of benefit, leaders convert qualitative goals into quantitative data points. Once plotted, the highest ROI projects naturally cluster in the top right quadrant. This visual consensus allows the organization to focus its resources on the project with the highest probability of success. Anchoring the prioritization to this scoring matrix provides an objective baseline for negotiation. It shifts the discussion away from subjective opinion and toward a documented consensus on capital allocation. But an optimally prioritized project on a chart still produces no value until it is adopted by the organization. This diagram identifies the 4 mandatory stakeholder groups that must be aligned for a high-priority project to be deployed. Success requires constant communication between the executive sponsors seeking ROI and the functional area leads who must integrate the model's outputs into their daily operations. Furthermore, the technical teams building the architecture must ensure the final output addresses the needs of the customer or client. These icons represent the specific soft skills a data science leader needs to manage these different groups. The most critical skill is translation, the act of converting abstract machine learning concepts into actionable business storytelling that the C-suite can approve and deploy. Serving as this translation bridge between technical execution and functional utility is the defining attribute of successful data science leadership. Once a project is prioritized and all of the key stakeholders are aligned, the organization must formalize the exact deployment sequence. This is the data science roadmap, the tactical result of the prioritization process. The matrix scores dictate the exact order of work. By documenting the strategic reasoning in this column, leadership forces the organization to commit to a specific path. This visual maps the first 100 days as a chronological sequence, identifying exactly when each project box is active. These nodes represent dependencies. Project 2 cannot begin until the infrastructure for Project 1 hits its documented milestones, ensuring resources are never spread too thin. This 100-day window provides a sense of urgency. It focuses the technical team on delivering a quick win that proves the project's ROI to executives. A chronological roadmap creates accountability. It prevents technical teams from spending months tweaking a model in isolation and forces them to deliver functional business value. However, a rapid deployment roadmap places massive strain on the company's existing technical backbone. This infrastructure grid must be built alongside your roadmap to support new data requirements. Leaders must invest in data governance to keep information usable and secure. Simultaneously, specific machine learning architecture is needed to automate model deployment so they don't degrade over time. Ignoring this architecture will cause the roadmap to collapse by day 101 as the weight of new projects exceeds the system's capacity. When these four pillars lock together, they form a solid organizational foundation for data science. The matrix provides the target, the team provides the momentum, the roadmap sets the pace, and the infrastructure secures the results. Success in this field requires the same rigorous scrutiny of capital allocation applied to any other major business initiative. Data science leadership requires the rigorous translation of computational power into structural, measurable, or